Hello, welcome to the course Transducers for Instrumentation. Last lecture we discussed some optical detectors uh, just like PIN diode and avalanche photodiode, and we discussed one type of optical source which is LED, the light emitting diode, which is very widely used for these optical power generation. The next important light source is the laser, which we are going to discuss today. The laser is a short form of light amplification by stimulated emission of radiation. So the word stimulated is a key word here which we are going to discuss today, how the light actually emission happening in a laser, which is different than a normal LED. Before discussing the lasers, we need to understand a little bit about some device physics, the properties of some material. So we have some sort of homojunctions and heterojunctions when we make the junctions in the semiconductor device. So we have two types of junctions. Homojunction means when we form a junction and the material on both sides of the junction is the same material, then we call it homojunction. And when the material is different on one side of junction is different than other side of junction, then it is called heterojunction. For example, when we make a silicon based diode, we say it's a p type material and we take an n type material, join them together, then a junction is formed which is called depletion region. If we see both the sides, though it is p type and n type on the other side, the material, the fundamental material, the base material is same, which is silicon. Silicon is p type dope on one side and n type dope on the other side, so it's called homojunction. However, if we take two different materials and we make a junction, so one side it's, let's say, gallium arsenide and one side is aluminum gallium arsenide, or some different material, some composition of the material is different, then we call it a heterojunction. And both these junctions have different properties. So we're going to discuss today what is homojunction and heterojunction, and then we will discuss the lasers, which is the optical source. So we have a homojunction both the p type and the n type regions are of the same semiconductor material. So in homojunction, both materials are same. In heterojunction, the junction layers are made of different semiconductor materials. So if we draw an energy band diagram for these heterojunctions, one side the band gap is larger. For example, we have, let's say, this kind of band where this band gap is Eg1. On the other side, the band gap is smaller. This is, let's say, Eg2. So now we have two different material. One side is Eg1 where we have high band gap, and other side we have Eg2 where this band gap is smaller. When we join these two materials, now the band need to be continuous because these are energy bands. Energy distribution is continuous, it cannot be discrete. So if we join these bands, they are going to join like this, and this. So here now we see there is a sharp change in the energy bands, and if we see here, we are making some sort of a notch here, or the well we call it. If we also draw the Fermi level for these p type and n type, because Fermi level is close to p type here, this is the Fermi level or EF. This is p side. Let's say we have positive charges here, and we have electrons here. This is EC and this is EV. Now in this energy band diagram, if we see carefully, this Fermi level is flat, and when we are joining these two different materials together, in conduction band there is a notch. This notch, or the well we call it, the tip of the lowest or the minima of this well is coming below the Fermi level, the EF, this dotted blue line which is Fermi level. The minima of this conduction band, or at this point, at this well, is coming below the Fermi level. It means this region or this notch or this well will always be filled with electrons, because this is below the Fermi level. So the probability of finding electrons here is very high. So all this well will be always filled with the electrons, and because these electrons are in the conduction band, so this on the top, this is a conduction band. These conduction band electrons are free to move, so we always have some electrons in the device at this point, this well, quantum well we can call it. These electrons are always available for the conduction. So without doing anything, without applying a bias, we just added two different materials, and because of the energy band, the difference in the band gap, we are creating a notch, a well, where electrons are freely available for conduction. So now if we apply a electric field in, let's say, perpendicular to direction of this board, these electrons will be free to move as per the applied voltage. So this happens in case of heterojunctions, because both the materials are different, the different band gaps, and we get these free electrons. Sometimes we call it the 2D electron gas, because these electrons are available. They are like uh, kind of liquid, or you can say the gas. They can move freely if we apply electric field. So these charge carriers are confined in a space away from the doping impurities. Hence, improved mobility, or the high electron mobility. So the difference between these heterojunction, where we are getting these electrons, this is different process than how we create electrons or the mobile charge carriers in normal MOSFET. The difference is, in MOSFET we do the doping in the channel so that we get these extra electron, the charge carriers. These are given by these impurities, boron or phosphorus, depending upon p type or n type. But the problem in doing that is, when we put impurities, the mobility of electron decreases, because there is a kind of imperfection in the lattice when we put these impurities, and these charge carriers need to travel in this channel, so the mobility decreases. However, in heterojunction we are not putting any impurity here, we are not doping the material at exactly at this quantum well. These electrons are here because of this because of the difference in the band gap. So these electrons are created by that, and these are away from the impurities, so they are seeing a perfectly fine crystal, and their mobility is very high, and this is the basis of something called HEMT, or the high electron mobility transistors. These are very high devices used for high speed applications, HEMTs. So this is the phenomena that leads to the HEMT devices, which is this two-dimensional electron gas. So now we know that gallium arsenide is a direct band gap material. Let's say we have gallium arsenide. This is a direct band gap material. And it emits in infrared. And for infrared, typically the wavelength is 870 to 900 nanometer. This is one material, and the other material is, let's say, gallium phosphide, which we know is a indirect band gap material. the band gap is around 2.2 electron volt. So here we have now two material. One is gallium arsenide, which is a direct band gap material, and the band gap is such that it emits in the infrared region. And another material is gallium phosphide, which is a indirect band gap. So these materials are also the mixture. For example, gallium arsenide material is nothing but gallium. When it is mixed with arsenic, then it's gallium arsenide, and which is a direct band gap. And when we mix gallium with phosphide or the phosphorus, then it becomes gallium phosphide, which is a indirect band gap material, and band gap is 2.2 electron volt. Now this arsenic and phosphorus both are in the group 3, so they belong to the same group in the periodic table. So this arsenic and phosphorus, they can also be mixed together. For example, we can have something called gallium arsenide phosphide, where we mix gallium with certain amount of arsenic and certain amount of phosphorus. So when all these three materials are mixed together, we call it gallium arsenium phosphide, GaAsP, with certain fraction of arsenic and remaining fraction of phosphorus. Then the effective band gap of this material, which is now the newer material made up of these three material, the effective band gap is determined by how much is the ratio of arsenic and phosphide in this complete material. So for example, we have both these arsenic and phosphide belong to same group in periodic table. It is possible to make alloy. Having composition of gallium, arsenic, the component of arsenic is 1 minus X, and phosphorus is. So we are taking X part of phosphorus and 1 minus X part of arsenic and mixing it with gallium, so that we are making a new component, which is gallium arsenic phosphide. Now the lattice constant of these gallium arsenide and gallium phosphide are quite comparable or almost equal, so we can mix them effectively. So the lattice constants of gallium arsenide and gallium phosphide are nearly equal. For X value less than 0.45, the alloy remains direct band gap with radiation in red and infrared. Red and infrared range. However, if we increase the composition of phosphorus, it means X is greater than 0.45, the alloy becomes indirect band gap. So this is a process of even converting a material or making a different material and tuning the band gap of this new material. For example, gallium arsenide has a fixed band gap of it's a direct band gap and which is fixed. Gallium phosphide is again a different material with a fixed band gap of 2.2 electron volt. Now we can play around with the composition of phosphorus and arsenic, and we can tune this band gap depending upon how much phosphorus we have in this material and how much arsenic we have. So depending upon that, we can tune the band gap of materials, and as we saw, for the composition of phosphorus, if it is less than 45%, the alloy remains a direct band gap material. It emits in red and infrared range. If we increase the amount of phosphorus more than 45% or X value is more than 0.45, the alloy becomes an indirect material. So we can see even how continuously this kind of proportion changes the band diagram. So let's say we have this graph where on the x-axis we have mole fraction, which is X value. This is 0 and this is 1, and in between we have, let's say this is 0.5, 0.2, 0.4, 0.6, this is 0.8 and 1. And on the y-axis we have energy band or the band gap. Starts from typically, let's say 1.5, 1.4 to 2.6, and it's a linear graph. So now we have two graphs. One is for the direct band gap, which starts from, let's say 1.4, and it goes like this. This is for the direct band gap. And the other graph is for indirect band gap, which comes like this. This is indirect band gap. So here we have two graphs, which one is for the direct band gap, one is for the indirect band gap. These are the values of the conduction band, and this is the difference between the value of conduction band and the top or the peak of the valence band. So we see as the mole fraction is changing from 0 to 1, these both of these graphs are changing, and whatever is the minimum voltage, minimum value, that will be the band gap of the material overall. So we see below 0.45, the red curve is below the green curve. It means that material will remain a direct band gap material for x less than 0.45, and higher than 0.45, the green curve is below the red curve. It means that material will become a indirect band gap material. So depending upon the mole fraction of how much phosphorus we add in the mixture, the band gap of material changes. So even if we reduce the mole fraction to 0.2, we can see the band gap is actually reducing compared to the band gap at 0.45 mole fraction. So this is how we can tune the band gap of material within a limit. So this is how we change the material, and changing the material band gap means that the light, the kind of which light it will emit, that also changes. So these indirect band gap materials are generally inefficient as light emitting diodes. So now let's discuss the optical source, which is laser. Laser is an acronym, so the full form of this is light amplification by stimulated emission of radiation. So laser is a device, and that laser is an acronym actually. So the full form of laser is light amplification by stimulated emission of radiation. So we are producing a light, we are amplifying certain photons, the photon energy, by stimulated emission of radiation. Stimulated is a key word here. We are stimulating the emitted photons, and they are generating further photons by stimulation. So we discussed earlier LEDs and photodetectors. So this is the difference between the photodetector. For example, if we when we discussed photodetector, we had their energy band diagram such that this is the conduction band and this is the valence band. EC, EV, and in photodetector we receive a photon from outside. A photon comes in, h nu, and it excites an electron from the valence band to the conduction band. So this is what happens in photodetectors. In LEDs or the light emitting diodes, we discussed we have conduction band and valence band. EC, EV, and there is a hopping of electron from conduction band to valence band. And in this process, this electron is actually losing energy, and this energy comes out in terms of a photon, h nu. So this is a photon which is being generated by this, the hopping of this electron from conduction to valence band. So this is kind of a reverse process happening in photodetector. So this is what LED. Now let's discuss the third case, which is lasers. What we have in laser is a conduction band and valence band. In laser we have so many electrons available here to jump down. So the primary requirement here is we have so many electrons here which are ready to jump from conduction to valence band. So when they will jump from conduction to valence band, they are going to lose energy in terms of photon. Now we have a photon which is there, which is generated elsewhere. Now this photon is traveling in the lattice, and there are so many more electrons available which are about to jump from conduction to valence, means they are about to generate these photons. So our original photon actually stimulates or affects these further photons, so that the emitted photon, the new photon which is generated from hopping, this photon is coherent with the originally available photon. So this is what it is called, the stimulated emission. So we, in this process, we have a photon which comes in, h nu, and at the same time one electron is jumping from conduction to valence. This is about to lose energy in terms of photon. Now this photon is actually reacting with this electron such that in the process it generates two photons now. This is the newly generated photon, and this is the original one which is on the left. Now it generates two photons. They are coherent, means all their properties are same. So this process is called stimulated emission. This is very particular to the lasers. The main or the necessary condition for this to happen is there should be so many electrons available in the conduction band, so that when a photon comes in at the approximately at the same time, one electron is there which is jumping from conduction to valence band. So it means we need to have lot of electrons available in conduction band ready to jump in. It means we need to have a very high concentration of electrons in conduction band, or we can say the population inversion. So we need to have a population inversion, which is the necessary condition for lasers to work. So this is the difference between LED and lasers. So this is the process happens in lasers. Now we saw that there is a something called population inversion, which is a necessary condition for lasing action. So let's discuss what this population inversion is. So in a semiconductor, population inversion can be obtained by means of high carrier injection. Which results in simultaneously heavily populated electrons and holes in the same spatial region. So now if we look at the band diagram for this material, we have, let's say, the conduction band, and we have the valence band. For example, this is our conduction band, this is the valence band. Now in normal case we have so many electrons available in the valence band. So this is the normal case where we have conduction band which is completely empty and the valence band which is completely filled now. Now we inject a high current so that many electrons has energy high enough so that they can jump to the conduction band. So remember in the earlier case, some of the electrons only have energy to jump to conduction band, and they were giving rise to conduction. Here in this case we have a very high carrier concentration which are jumping to conduction band, or this is called the population inversion, where the complete a top layer of valence band, completely all the electrons jump to the conduction band and remains in the conduction band. It means the conduction band is completely filled on the top. However, a valence band is empty in the bottom. So if we apply a population inversion here, after population inversion the bands look something like this. This is valence band, conduction band, and this layer, all the electrons jump to the top, and leaving behind a completely empty layer in the valence band. So if we can see whole of this area, this whole population actually have migrated to the top, which is here. So this is called the population inversion, where all the electrons in the valence band, they have jumped to the conduction band, leaving behind a complete layer of empty states, and all the states in the conduction band are now filled with electrons. So we see here now we have so many electrons in the conduction band, and these conduction band electrons, they can lose this extra energy anytime, and they can jump back into the valence band anytime and give rise to the photon. So this is called the population inversion. Now the incident photon, which is coming from the left, if the incident photon with energy h nu, this is the energy of photon. If this energy is greater than Eg, the band gap of material, but it is lesser than Ec minus Ev, the difference between conduction and valence band. If the photon energy is such that is between Eg and Ec minus Ev, this cannot be absorbed. So to understand this, let's draw this diagram again. We have a conduction band, and we have valence band, and we have population inversion. It means we have many electrons in the conduction band. All these states are filled, and in the valence band all the top layer is empty. This whole layer is actually empty. There is no electron in the valence band at the top layer of valence band. This is no electron. Now one photon is coming from the left. Now this photon, it can not be absorbed if the energy of this photon is higher than Eg but lesser than Ec minus Ev, because to absorb this photon, a electron need to be present here somewhere so that it can jump from the valence band to conduction band and absorb this photon. This is not possible because there is no electron available here. Electrons are further down in the valence band, so they cannot absorb. They need more energy compared to what energy photon has to jump to valence band. So this photon will not be absorbed by the material. However, at the same time, so many electrons are there which are ready to jump down to valence band, emitting a photon. So in this process, this photon actually interferes with the energy emission of electrons and generate one more photon. Because of this hopping, these both the photons are coherent or the same in all the characteristic. How they interact to each other, that is beyond the scope of this course, but this photon actually reacts or interfere with the hopping of electron and generate another photon. So let's say we have now this electron which is jumping down to empty state here, and in this process we are generating two photons. This is h nu and this is another photon which is h nu. So when these two photons are generated, again they are propagating in the same channel. Now other electrons are ready to jump. For example, this electron is also ready to jump from top to bottom to this empty state, and this also reacts with these incoming photons. So let's say these two electrons are jumping down, emitting a photon, and two photons are coming from the left which interferes with this emission of photon, and at the end we get four photons of exactly same characteristics. So this process is called amplification. By stimulated emission. And the conduction and the necessary condition for this to occur is the condition for stimulated emission underpopulation inversion is the energy of incoming photon should be greater than Eg, the band gap of material, but it should be lesser than the difference between Ec minus Ev. So this is the necessary condition for laser action. So this is how the laser device works. In this we have a population inversion where all the electrons in the valence band, they jump to the conduction band because of the very high current flowing or very high and very high charge is provided to this lattice. Now these electrons on the conduction band, they are ready to jump at any time, they are continuously jumping. Now if a photon comes in where the photon energy is higher than the band gap, so it can be absorbed, but it will not be absorbed because there is no electron available right on top of valence band which can take this amount of energy and jump to conduction band, because there is no electron available in the valence band and there is no empty state in the conduction band where it can jump. So this photon will not be absorbed on, in fact this photon will not be absorbed, but at the same time if electron is jumping down emitting a photon, this incoming photon will react with interfere with this release of energy, and the resulting photons are identical in nature. So this one photon gives rise to two photons, which is an amplification. One photon becomes two and both are same, and these two photons further react with two jumping down electrons and create four electrons which are again of the same properties, and there is further amplification from 2 to 4. So this is called the amplification by stimulated emission, because here the photon is interacting with a jumping down electron and releasing the same kind of photons. So we call it amplification by stimulated emission. So this is how a laser device works, and the condition for stimulated emission is h nu, the energy of photon should be higher than the band gap, but it should be lower than Ec minus Ev, the difference between the Ec, the conduction band and the valence band, and at this point this is EFC, and let's say we call it this EFV. So this is in fact EFC minus EFV. How many electrons are jumping from top to bottom, that dictates what is the value of EFC and EFV. So this is the condition for stimulated emission. Next we discuss a little bit about the waveguides. We can make these waveguides where light can travel in those waveguides on chip, and light will travel through total internal reflection, and these can be made using microelectronics processes. So we can make something called waveguides to carry photons from one place to other, and making of this is very simple. If we have a PN junction This side is, let's say, p type, this is n side, and this is the junction or depletion region. Now we see this region, which is depletion region. This does not have any moving charge carrier available here. It means the property of this material is different than p side and n side. So if we measure the refractive index of this material, along this direction, if we measure the refractive index will come out like this. So this is refractive index. In this region the refractive index will be different because this material does not have any charged particles. So in this region this refractive index is different. So if there is a change in the refractive index, it means we can compare it with the optical fiber where we have core which is of different refractive index and we have cladding which is of different refractive index. And now if we shine a light in this structure along this direction, more of the photons will be confined in the center region. So if we shine a light in this structure, many of these photons will be confined in this region. These are the photons confined in this depletion region, and this can act as a waveguide. All these photons will be traveling from one side to another within this structure itself. So we can say the electron hole concentration in the depletion layer modifies the refractive index creating a waveguide. Which helps to confine the photons. So here we have a structure where we have p and n type material. When we join them together, they form a depletion layer, and because this depletion layer is different than both of the materials because it does not have free charged particles, so there is a slight change in the refractive index of this depletion layer compared to both the sides, which is very similar to our optical fiber where we have a core which has different refractive index, and on the cladding which is surrounding this which has different refractive index. So just like our optical fiber carries these photons or confine all the photons in the core itself, the same structure if we shine the light here, the photons will be confined in the depletion region because of this difference in the refractive index. So today we discussed the lasers, and before that we discussed homojunction and heterojunctions, and we saw for the lasing action we need a population inversion, and we saw the necessary condition for lasing action, and then we saw the waveguides where we can confine these photons. Instead of optical fiber, we can use waveguides, which is easy to make on chip when you are making these using microelectronics fabrication process. It's easy to make waveguides on the wafer. So this is all for today. Thank you.